Okay, we're going to do a spring mass example here. So we've looked at a couple in class, so this is just another kind of variation with some different constants that we have here. So we have our basic differential equation model. That we looked at in class, why that is what describes this kind of situation here. So we need to think about the constants and then initial conditions that are described, and then we'll analyze the solutions to this differential equation. So we're given a mass of 0.2 kilograms. We're given a damping constant of C equals 8.4 kilograms per second. And we're given some information that allows us to find K, although we're not explicitly given K. So we'll need to do a little scratch work over here to find our K value. So that's the spring constant. So we use Hooke's law, and we think about the forces. It tells us here the mass that stretches the spring to its equilibrium position. So that's what we're going to use to find our value of K. So we're using the relationship that the force due to gravity is going to be equal to the resistive force of the spring when it's at equilibrium position here. So this is the force due to gravity, mass times the gravitational acceleration due to gravity. And then K, that would be the spring constant, and L is the amount that the spring is stretched. So I'm going to use 9.8. You could use 9.81 if you want to be even fancier here, but I'm going to use 9.8 for gravity. M is 0.2. K is what we're trying to find, and then L is the amount that the spring is stretched to get to equilibrium. So I do have to be a little bit careful here. Notice that that distance is given in centimeters, and so I need to be consistent with my units here, meters, kilograms, and seconds. So I need to write that in terms of meters, so that will be 0.04 meters. And then divide through by 0.04 and solve for K. We're going to get K equals 49. So that's going to be what we're going to put in for K over here in our differential equation. So sometimes they'll give you that K value. Sometimes you'll need to figure that out. Units on that is kilograms per second squared. I guess I could have thought about that if I would have looked at the differential equation here. All right, so we're given all of these, and then we're going to just put them into the differential equation, write down our initial condition, and then analyze the solutions here. So 0.2 y double prime plus 8.4 y prime plus 49y equals 0. It tells us that when the spring is set into motion, it's stretched 5 centimeters from its equilibrium position. You have to read the problem carefully. Sometimes the way it's worded, they'll give you some information in part of the problem about how far it's stretched to get to equilibrium, and then maybe it's not stretched more, or they'll tell you it's stretched a total distance from its original position. But really what you want to measure here for the initial position is where it is from equilibrium. So here, that's that 5 centimeters more. It's stretched 5 centimeters more. So in terms of meters, again, just like here, I have to be careful about my units, 0.05 meters, and it's released from rest. So the initial velocity, y prime, is 0. All right, so here's our differential equation and initial conditions, and we're going to just go ahead and solve this. So these are pretty straightforward to solve. We've got constant coefficients. We're just going to write our characteristic polynomial. Just write that in a different color here. So the characteristic polynomial, 0.2 r squared plus 8.4 r plus 49 equals 0. Want to find the zeros of this characteristic polynomial. That'll help us write down our solutions here. So this one, written in that form, it's maybe not super easy to see, but if you multiply through by 5, then I can't do that in my head, but I did do that on my scratch paper here. So if you multiply through by 5, you get r squared plus 42r plus 245 equals 0. And I finagled this problem a little bit to make the constants nice in terms of real physics problems. Often the numbers come out a little uglier than they're going to here. This one happens to factor. In general, that's probably not going to happen, and you're going to have to use quadratic formula. But this one does factor into r plus 35 and r plus 7. A lot of the textbook homework is like that too. The numbers are sort of a little massaged to make sure that they turn out reasonably nice so that you don't get hung up in some messy calculations and you're able really just to focus on analyzing what's going on. But in terms of real applications, you know that these numbers probably are not going to come out quite as compatible with each other as they did on this problem. All right, but I get two zeros, negative 35 and negative 7. Real, distinct zeros for the characteristic polynomial. So we know how to use those distinct zeros of the characteristic polynomial to write our two linearly independent functions that we need to solve the differential equation and write the general solution. So go ahead and put that here. So for our real distinct zeros of the characteristic polynomial, remember that e to the rt will be your two linearly independent solutions. With a general solution, we are given some initial conditions here, so we can use those to help find the particular solution satisfying the initial motion of the object. So we'll need to take a derivative and plug in our initial values here. I'm going to go ahead and put a box around this because I want to talk about it a little bit more. But you can go ahead and, let's see, I'll squeeze that in right here. Y prime is negative 35 c1 e to the negative 35t minus 7 c2 e to the negative 7t. So you put in your initial conditions for each of those. You get a system of equations, which is not necessarily easy to solve in your head, but it's fine if you use technology to help you solve that. So let's see, what will we have here? We'll have 0.05 when I put in for y equals c1 e to the 0 plus c2 e to the 0. And then for the other one, we'll have 0 equals negative 35 c1 e to the 0 minus 7 c2 e to the 0. To solve that system, which I did separately, and I got my c1 is negative 0.0125 or negative 1/80th. Either one is fine. C2 is 0.625, 0.0625, which is 1/16. And so we put those in, and we can write our general solution either with the decimals, or I'm just going to use the fractions here for my coefficients. So y equals, make sure you put the right constant in the right place, negative 1/80th e to the negative 35t plus 1/16 e to the negative 7t. All right, so that's our particular solution that models the motion of this system that was described at the beginning of the problem. But the other thing I want to talk about here is just kind of noticing that when I find real distinct zeros of the characteristic polynomial, whatever the actual numbers turn out to be, as long as these are real distinct zeros for that characteristic polynomial, the nature of your solution is going to be similar. And so just kind of talking about that a little bit more globally, what exactly is going on when you have this type of solution. So if you think about what's happening here, I don't have sine or cosine functions. The other examples we looked at had sine and cosine functions in their solutions, which indicated we had repetitive motion, bouncing for the motion of the object on the spring. These do not. What these are going to do is just approach 0. When t gets larger, everything in here is going to approach 0. And again, whether you have exactly these numbers or some similar situation here, you're going to have a situation like this where these solution curves are not going to bounce. They're going to just approach 0. And so you've got an initial position, in this case, of 0.05 meters, and that solution curve is going to approach 0 without bouncing. And it is possible that it might pass through equilibrium once and then approach 0. Without just looking at this and doing any analysis of it, I can't necessarily tell which of these two situations it's going to be. But the key is that I won't have repeated bouncing. I don't have the sine and cosine functions in here that would cause those repeated oscillations. Either of these two sort of typical types of graphs here are what are called an overdamped system. I have enough damping, enough resistance in order to stop the bouncing. So there is no bouncing. It is an overdamped system. How you can determine which of these two situations it is you would be looking at the specific numbers in the problem and the analysis of the problem here. And what you'd be looking for is there a value of t, this would be a t value that is greater than 0 when y is equal to 0. And so if you set the equation, if you set y equal to 0 and attempt to solve for t, it's not easy to solve for t because of the t in both of these, but you can do numerical approximations if nothing else. But this would be a t value that's greater than 0 where y is equal to 0. In this particular problem, you don't get one. The t value that you get is negative. It's not a positive value of t. So in this particular problem, we actually end up with this sort of graph here. But it is possible, depending on the numbers and how they turn out, that it might pass through equilibrium once and then go ahead and approach equilibrium after that. So we've looked at really 3 examples, a couple of them in class and now one in the video, where we looked at underdamped system, an undamped system, an underdamped system, and then an overdamped system. So they're also critically damped systems, so there are some of those in your homework. Make sure you look through that. And we talked about that vocabulary in class as well. But just kind of thinking about the different types of motion that you get, which all has to do with what was happening here, this damping constant. This one was a pretty large damping constant. We had a lot of resistance here in this system, which is what caused this system to basically just approach equilibrium without having that repeated bouncing. When we looked at an example where we had a smaller constant here, we had repeated bouncing. Even though it did eventually stabilize and approach 0, the bounces got smaller, but it did keep bouncing over and over again because we had a smaller constant there. And of course, if you have 0 for that constant there, then you're just going to get repetitive motion over and over again. All right, so try some of the homework like this, and remember to look back at your notes. There's a lot of vocabulary that we went over in class, so be sure to look back at your notes for that vocabulary that's going to be relevant when you do some of your homework, so some of these vocabulary words that we talked about in class.